All right, number 10. 1210. Is that the one that had the picture? Yeah, that's this one. Pulley C and D are attached to shaft AB. As shown, the shaft is supported on bearings at each end. Shaft rotates. Ah, so it's free to rotate, right? So this end's free to rotate, and this end is free to rotate. Pulley D is the driver, pulley C is the power takeoff. The diameter of the shaft is 2.5 inches. Calculate the belt tension, P3. Well, that's kind of fun. A little statics problem first. And then this shear stress. So the first thing I want to note is end A and end B are free to rotate. So out here and out here, there is no stress. It's just rotating. The only stress is between the two. Okay, so let me draw it real quick. 30-inch diameter here. And a bigger 38-inch diameter here. Shaft between. And then some forces, 60. P3. 80. And 360. That looks like it. So the first question was, oh, what's P3? Got to be in equilibrium, right? So we just have to calculate some moments. We need to know how much moment is here. However much moment is here has to be carried here in order for this thing to be in equilibrium. So we got 80 pounds, 360 pounds, 38 inches diameter, and 30 inches. So I would calculate moment here first. Looks like it's much bigger this way. 360 is a lot bigger than the 80, right? Maybe I'll call this point D. So moment at D is going to be 80 times half of 38 is 19. And that one looks like it's rotating in a negative direction. And 360 times 19 in a positive. That gives me moment at D. You got what? 1520? Oh, okay. You're probably ahead of me here. I got 5320 here. Okay. Inch pounds. So that means this has to come to 5320. So I'm going to do sum of moments over here. Has to equal 5320 inch pounds. Has to equal 60 times 15. And that one is plus. And P3 times 15. And that one is minus. So then we need some algebra to figure P3 out. So first thing I would do is take this, move it to the other side. This is 900, gets taken away from the 5320. Whoops. And then I got to divide by 15. $294.66. Anybody else get that? That's what P3 is. So yeah, a little statics problem there. Took me a second, like, oh, what do I got to do here? Oh, I got to put it in balance here. So the interesting thing is knowing that with a bearing out here, right, some kind of bearing and some kind of bearing, and these free to rotate, this thing has to be in balance. It can be a constant RPM, that's fine. That's in equilibrium, a constant. And I think they did mention that, right? The shaft is supported on the bearings at each end. The shaft rotates at a uniform speed. Boom, that is equilibrium. So a car traveling 100 miles an hour is in equilibrium as long as it's not accelerating or deaccelerating, right? So this thing is in equilibrium, which means the moments have to equal 0 all over the place. So that means this moment here, 5320, also has to be this moment here, 5320, in balance with each other. So that means in the shaft, in the middle between them is feeling 5320 for a torque, which is what we need to calculate maximum shear stress in the shaft. Because a rotating shaft, that is torsion. Torsion is TC over J. Torque, 5320 inch-pounds. C, we need the diameter of the shaft. I think they gave that to us. 2.5. So half of 2.5 is 1.25. Because we need C, which is half the distance. And then we need J, the polar inertia for a solid circular shaft is pi d to the 4th over 32, or 64, 32. So we know D equals 2.5. Anyone else get that? I'm crunching. $2.5. I got 1734.05 PSI. Yep. Did they give us the material? What it's made out of? No. Problem stinks. That's a good problem. Wish they'd toss in the material so we could say, oh, great. It's made of steel. We have a factor of safety of like 25. It is free to rotate on the ends, but in between, it's carrying that load. Yeah. So in between, right between there, it's carrying that torque, which are actually opposed to each other. So it's the material that's resisting that 5,000.
So we're finding the stress.
Yep. Nothing out here. These ends are free to spin away all they want. But in between is feeling the moment resistance of these two moments. Yeah. It's tricky. When you first start looking at these, like, oh, this is tricky. What's loaded, what's not loaded? Yeah, yeah. And then anytime we calculate a stress, we really should be looking at some table to say, oh, that's good or not good, but they didn't give us material. So, you know, if the thing was made out of wood, it was a wood shaft, be like, this is not gonna work. So, yeah, it's all right. My job is to keep reminding you that when we calculate a stress, we're doing it for a reason. Like, is it good or not good? And that you will have that question on the test where you can, like the P over A, you might have to calculate a stress and then tell me what you think of it. That means look at a table and say, oh, it's way under the yield. Excellent. See you all Thursday. You'll kill it, I'm sure. It's just the regular old stress, but I stick a Y on it. So that's tensile stress. I just do a little Y for yield stress. Yeah, I don't think they give you anything in the table. They just label it. Oh, they do. They do F of Y. Yep. Yeah, why do they do that? That's a very good question, Nick. This book does not use F for stress. This book uses the symbol sigma for stress. Now, why doesn't the table have that? Well, they probably took the table from some other source. I don't know. But yeah, that's. Yep. Yes, sir. Yep. It is the max for the elastic limit. Yep. Nope. Yes. The ultimate stress would be the point at which it snaps. That's a great question right there. Question for the stress strain diagram. Where's the point in which it actually fails? All right.